3 astronauts left a recorder running on the lunar surface. No one told them what to do if it picked up something it was not supposed to. In November 1969, the seismometer planted by the Apollo 12 crew began detecting vibrations unlike anything the geologists back in Houston had modeled. The moon, the airless, geologically dead moon, was ringing. Not metaphorically, literally vibrating, like a bell, for over an hour after the ascent module crashed into its surface. And it kept doing it, over and over, across multiple missions, with variations in frequency, duration, and origin that no one has ever fully explained to the public's satisfaction. Before we get to what was recorded, you need to understand what silence sounds like in space, because the sound NASA captured was not silence. The surface of the moon is, by every measure of physics, one of the quietest places in the solar system. No atmosphere means no medium for acoustic waves, no wind, no rain, no tectonic plates grinding against each other. If you stood on the lunar regolith and dropped a hammer, you would feel the vibration through your boots, but you would hear nothing. The moon does not carry sound. That is the foundational truth of lunar geology, which is precisely why what the Apollo 12 seismometer recorded in November 1969 broke something inside the scientific consensus. Pete Conrad and Alan Bean had just ascended from the lunar surface. Their ascent stage, the upper half of the lunar lander, the module that carried them back to orbit, was deliberately jettisoned and sent crashing back to the moon at roughly 3,700 miles per hour. This was intentional. The plan was to use it as a calibration event, a known mass, a known velocity, a known impact point. It would give seismologists a baseline, a controlled reference, something to measure against. What they measured was not what they expected. The moon rang for 55 minutes. Not a sharp spike followed by immediate decay, the signature you would expect from a rock hitting rock, or even a large meteorite impact. The seismic signal built slowly, peaked, and then faded across nearly an hour in a pattern seismologist on Earth had never seen in natural rock. One geologist at the time described it in his report as analogous to a bell. This is not a metaphor coined decades later for documentary narration. This is in the original 1969 mission data. The word used was reverberation. Here is what reverberation means in geological terms, and why it matters. On Earth, when seismic energy travels through rock, it scatters quickly. The rock is not uniform, it is cracks, water pockets, mineral variations, soft sedimentary layers. Energy dissipates fast. If you hit a rock with a hammer, the vibration is gone in seconds. But if the interior of the moon behaves more like a crystal, homogeneous, rigid, with very low internal friction, then seismic energy has nowhere to scatter. It bounces. It resonates. The moon, if this interpretation is correct, is not a dead rock. It is a hollow-sounding instrument. The question NASA could never fully answer was, hollow with respect to what? The Apollo 14 crew amplified everything. In February 1971, Alan Shepard and Edgar Mitchell, the fifth and sixth humans on the moon, carried a more sensitive seismograph. Their mission coincided with a series of natural moonquakes, and the data they returned revealed something that quietly destabilized the standard geological model of the moon's interior. The moonquakes were not random. They occurred in clusters, not just temporal clusters, geographic ones. The deep moonquakes, which occur somewhere between 700 and 1,200 kilometers below the surface, were emanating from approximately 300 distinct locations, and those locations were repeating the same spots over and over, with a periodicity tied to the moon's elliptical orbit around Earth. Edgar Mitchell spoke about this late in his life with a kind of controlled urgency that stayed just inside the bounds of respectable science. He did not make extraordinary claims. He simply said that the data never received the public analysis it deserved. Mitchell was a man with a doctorate in aeronautics and astronautics from MIT. He had walked on the moon. He had floated in the void between it and Earth, and experienced something he spent the rest of his life trying to articulate. When he said the data was under-examined, people who had worked the Apollo program did not entirely disagree, because what the seismographs recorded between 1969 and 1977, when the last Apollo-era lunar seismic station finally went offline, included events that fit none of the standard geological categories. There were deep moonquakes. Understood. Tidal stress from Earth's gravity, accumulating along fault planes, releasing in clusters. Plausible. There were shallow moonquakes, sudden, violent events in the crust, some releasing energy equivalent to a magnitude 5 earthquake. Unexpected, but eventually fitted into models of thermal expansion and contraction as the lunar surface heats to 250 degrees Fahrenheit during the 2-week lunar day and plunges to negative 280 degrees during the lunar night. There were meteorite impacts, cleanly identifiable by their surface origin and immediate spike signature. And then there were the events that do not fit cleanly into any of those categories. The ones that generated long-period signals from locations that did not match the mapped deep moonquake zones. The ones that showed a directionality, not the omnidirectional scatter of a thermal event, but a sourced signal with a vector. These are the events that appear in the raw Apollo seismic archive, logged, time-stamped, and never fully classified. In 2006, a team of researchers at JPL, the Jet Propulsion Laboratory, Pasadena, published a reanalysis of the Apollo 12 seismic data using techniques that did not exist in 1969. Their finding, published in the journal Icarus, was that the original analysis had actually underestimated the complexity of the signal. The 55-minute ring was not a single wavefront bouncing around a hollow sphere. It was multiple overlapping wave modes, body waves, surface waves, modes that implied an interior structure significantly different from Earth's. The moon's seismic properties, they concluded, were not explained by any model then current. That paper was not widely covered. Here is what it would have felt like to be Frank Press, the geophysicist who first processed the Apollo 12 seismic data in 1969. You were sitting in a lab at MIT. The tape comes in. You run it through your instruments. The signal you expect, a sharp impact, a rapid decay, is there for the first few minutes. And then it keeps going. You check the equipment. The equipment is working. You call your colleagues over. They stare at the same readout. The moon is still vibrating. 40 minutes in. 50 minutes in. 50 minutes in. Press later told colleagues he had the sensation of the data being wrong, not because he thought the instruments had failed, but because the alternative was that something about the moon was fundamentally not what they thought. He was right. Something was not what they thought. What the combined Apollo seismic network eventually revealed is this. The moon has a layered interior, but not a simply layered one. There is a crust thicker on the far side, thinner on the near side, probably between 34 and 43 kilometers deep on average. Below that, a mantle of some kind. Below that, possibly a small partially molten core. But the seismic attenuation, the rate at which seismic energy is absorbed by the interior, is so low in the upper mantle that signals travel enormous distances without losing significant energy. This is why the moon rings. Not because it is hollow, but because its interior is extraordinarily efficient at transmitting elastic waves. The material has almost no internal friction in the relevant frequency range. It behaves, seismically, more like a crystal than like terrestrial rock. The question that these raises, the one that connects directly to the events NASA never fully explained, is where that efficiency comes from, and why certain events produce signals that do not match the model. The last Apollo seismic station went silent in September 1977, shut down as a cost-cutting measure. For 27 years, there was no active seismometer on the moon. The raw Apollo data sat in archives. Some of it was digitized, some of it was not. The full data set, thousands of hours of seismic recordings, was not comprehensively reanalyzed with modern algorithms until the mid-2000s. And when researchers finally did apply those algorithms, they found events in the historical record that the original team had flagged as anomalous, and then, under the pressure of data volume and limited computing power, set aside. Set aside, but not discarded. Still there. Waiting. In 2019, the InSight lander placed NASA's first seismometer on Mars. It worked. It detected Mars quakes. It is, to this day, producing data about the Martian interior. The scientific community declared the moon was the logical next step. The Lunar Geophysical Network, a proposed array of 4 next-generation seismometers to be placed across the lunar surface, has been in planning stages for years. It would generate, in its first month of operation, more seismic data than all the Apollo stations combined. It has not yet been funded. There is something quietly devastating about that fact when you sit with it. The moon is less than 400,000 kilometers away. We have touched it. We have walked on it. 12 human beings stood on its surface and looked back at Earth and felt something that no language has yet adequately described. And yet the most basic questions about what the moon is made of, how it formed, and what is happening inside it right now remain open, not because the science is too hard, but because the instruments we left behind were switched off and not replaced. The events NASA recorded on the moon, the rings, the anomalous signals, the clustered deep moonquakes from repeating sources are not secret. The data is in the archive. The papers are published. The anomalies are acknowledged. What they are not is explained, fully, satisfactorily, in a way that closes every open question and produces a model with no residual events. Science is comfortable with that. Science calls it an open research problem and moves on to the next funded priority. But there is a specific category of anomaly in the Apollo seismic record that sits in a different position from the rest because the researchers who flagged it did not just call it anomalous. They called it unclassified. In the taxonomy of lunar seismology, an unclassified event is one that cannot be assigned to any of the known source mechanisms: deep moonquakes, shallow moonquakes, meteorite impacts, or thermal events. The Apollo network recorded at least 28 such events over its operational lifetime. A handful were not. And the small number of those, the exact count varies depending on the analysis threshold applied, originated from locations that are inconsistent with the geological structures we have mapped, not from the far side, where a large impact could have gone unobserved. From the near side. From within the network's detection range. From positions that should have produced identifiable surface or deep source signatures if they had a mundane origin. Jack Schmitt walked on the moon in December 1972. He was the only professional geologist to do so. All the other Apollo astronauts were test pilots who received geological training, but Schmitt had earned his doctorate at Harvard. He has spent the decades since Apollo attempting to explain lunar geology to a public that, he has noted with barely concealed frustration, stopped paying attention the moment the last Saturn V rocket stopped flying. When asked about the seismic anomalies, Schmitt does not dismiss them. He says the moon is more complex than the models suggest. He says the interior is probably differentiated in ways we have not yet characterized. He says the data deserves more attention than it has received. He is 89 years old. He's the last living person who has held a moon rock while standing on the moon. What NASA recorded on the moon between 1969 and 1977 is not a mystery in the conspiratorial sense. There is no cover-up. The data is accessible. But it is a mystery in the most rigorous scientific sense, a set of observations for which the current best models do not provide a complete account. And the specific category of unclassified events in the Apollo seismic archive represents something rarer than a cover-up, an acknowledged gap in our understanding of an object we have physically visited that sits at an average distance of 314,400 kilometers from the surface of the Earth, and that we have not yet deployed the instruments to properly investigate. The moon rang for 55 minutes in 1969. It rang again in 1971. The signals that cannot be classified still sit in the archive, time-stamped, preserved, and waiting for the seismometers that have not yet been built. When the lunar geophysical network finally reaches the surface, if it reaches the surface, it will not just answer new questions. It will have access, for the first time, to the spatial resolution needed to trace those unclassified events to their source. To locate them, not just in time, but in space. To look at a map of the moon and point to a place and say, that is where the signal came from. That is the moment that will either close the question or open one far larger. The moon is not finished surprising us. And if the next layer of what it is hiding turns out to be geological, that will be fascinating. If it turns out to be something else, something the geological models do not account for, that conversation will be very different from any we have had so far. If you want to understand what the lunar geophysical network would actually detect when it reaches the surface, and why the specific frequency range of the unclassified Apollo events matters more than the events themselves, that is exactly where this goes next.